Okay, this time our heat equation has something called a Neumann condition. This one's called a Neumann condition. And you call it a Neumann condition because it has a condition about its derivative, not the value. So in the previous case, when we solved the heat equation, we didn't have a sub x. Sub x means partial with respect to x. We didn't have this, and you just had the value fixed to 0. That's called Dirichlet condition, as opposed to Neumann condition. And to explain what this derivative is doing, I need to draw this picture. So you have this length 8-meter rod, and it's inside an insulation. Insulated here and there, so it becomes a one-dimensional problem. And not only that, it also has this insulation at the end. So, because there is no heat going out or coming in, same thing over here, there's nothing going in or coming out. If you look at the temperature at the end, it kind of, so originally it's going to happen like this. Originally, the initial temperature distribution is like -6 here, and when it's 8, -8 plus 6 gives you +2, so it's like this. So that's what happens when time t is equal to 0. And then when time passes, the heat will try to even out, right? Oh, sorry, I got it backwards. This should be +6 and -2. It's like this. Sorry about that, right? If you plug in 0, you get 6. If you plug in 8, you get -2. Okay, so that's what happens at time t equals to 0. And then when time passes, things will try to even out, right? So this is going to come down. That's going to come up. And it will be something like this. And then gradually it's going to even out. And the thing is, instead of being 0, it's going to, because it has more higher temperature over here than negative temperature here, so at some point it's going to have a finite temperature. So at time infinity, when infinite time passes and all the temperature distribution on this rod becomes uniform, it will get closer and closer to a certain flat temperature which is not 0, which is same as the average temperature you started with. Because everywhere it's insulated, the average temperature that you started with should equal to the average temperature you end. So that's what you think. So that's the first observation that you have. And then another thing is, when it's insulated out here, because there's nothing going out or coming in, if you look at the shape of the temperature distribution, it will be 0. It will be the slope will be 0 at the endpoints. Okay. So if you take the partial with respect to x at the boundaries, over here on the left side or over here on the right side, they're both going to give you 0 as the derivative. So that's what Neumann condition is. So this tells you that it's insulated. The difference between the Dirichlet condition and this one is, if you don't have the x, then immediately, even if you start from something like this, immediately the endpoints immediately falls down to 0, like this, because it gets cooled. So it almost instantly comes down to 0, and then starting from there, the heat just dissipates away, giving you everything as 0 at time t infinity. So in Dirichlet condition, regardless of your initial temperature distribution, the distribution at time infinity will always be just 0 everywhere, assuming that at endpoints are always kept to 0, if that was the condition. For the Neumann condition, at time t equals infinity, it will be a uniform distribution with the temperature being the same as the average temperature that you started with, because there's no loss in heat. Okay? Any questions here? Does it make sense? All right. Now, let's see. Now let's try to solve this using the separation of variables method. What does this anyways? What's the separation of variables? You remember? What's the assumption? No idea?
So fx times gt.
You think of it as a function of x times function of y. Now today I'll use a slightly different notation, which is also a notation that's used a lot. So I'll use capital X for the function that is only dependent on x, and I'll use capital T for the function that's only dependent on t. You plug in on the left side, so you get on the left side you get x t prime of t equals to 7 times x double prime of x times t of t. And then you divide everything by 7xt, which gives you t prime over 7t equals to x double prime over x. I'm being a little lazy here. I should really be writing t prime of t and 7t of t and x double prime of x and x of x. Sometimes you just write down the function assuming that you know what it is. And the advantage of naming the functions with their variables is that now you see that on the right side you have function of x only, left side you have a function of t only. When can that happen? When can a function of t equal to a function of x? Yes?
When it's equal to a constant.
When it's equal to a constant. That's the thing. Very good. And then you set that constant equals to negative lambda. The reason for doing that was because if you do that, this turns into an equation that we've been solving before. X double prime equals to negative lambda x, which is x double prime equals to plus lambda x equal to 0. Now the boundary conditions. These boundary conditions translate to the following thing. Because this is a partial with respect to x, if you take this and differentiate by x, only x becomes differentiated. And you're plugging in 0 to x, so that becomes 0, where tt survives. Okay, so this is what you get if your uxt is this. So if you take this as uxt and plug it into the left side, take the derivative with respect to x, and you plug in 0 into x, then that's what you get for this part. Okay. Now, what would you get for this one? Can you tell me? Yes? X prime of 8, t of t. And that's equal to 0. Now, let's make an argument. Can t of t equal to 0? What's bad if you set t of t equal to 0.
Trivial.
You get a trivial solution. Very good. So that gives you uxt trivial. So that's no good. And therefore, you can't set this equal to 0. So what's your only option? X prime of 0 should be 0, and x prime of 8 should equal to 0. So those are your options. Okay. And putting these two together, we have an endpoint value problem of finding eigenvalues and eigenfunctions. Right? All good? And again, I'll skip this process. There are some calculations that we did before, although this value may be different. We did do something similar. And the outcome of that was that such a function that has 0 derivative at the endpoints are what? Sine or cosine?
Sine.
The sine has value 0 at the endpoints. Okay? It would be cosine. Cosine with length L equals to 8 should be what? Cosine n pi x over 8. Okay, so these are the functions whose derivative at 0 gives you 0, and also when you differentiate this and plug in 8, you get 0. So these two conditions are met for this one, and we also know that if you plug it into here, what should lambda be? So your x of x should be this one. What's your lambda? If you differentiate this twice, what do you get?
1 over, no, 8.
N squared pi squared over 64, right? With a minus sign. But if you let this to be the plus one, and when you plug it in here, you get 0. So these are the values that you get when you solve the eigenvalue problem. And of course, we were talking about some free constant here, but you don't need it. Okay. So this is what we get for xx. So these are the functions that satisfies this condition, with lambda being this. Okay. Here, n should be what? N is? Can n be 0? Yes. Yes, because if n is 0, you get a constant, and constant satisfies this. With lambda 0, and this is satisfied, this is satisfied. So n is allowed to be 0. This is different from the case when we had the Dirichlet condition. When you had x of 0 equal to 0 instead of x prime of 0, in that case the eigenfunctions were sine of n pi x over 8 with lambda same, but n should start with 1. That's what we found out for the sine case. For the cosine case, we have n starting from 0. So n equals 0, 1, 2, and so on. And then we plug this back in here and solve this equation, which is t prime equals to, if I multiply this to the other side, that's negative 7 lambda t. Right? Multiplying this to the other side, that's what we get. And what kind of function gives you this when you differentiate? It's e to the negative 7 lambda t, right? If you have such a function, if you differentiate, you get negative 7 lambda in front, right? So exactly this one. And because lambda is this, we can rewrite this as e to negative 7 n squared pi squared over 64t. And that's one such function that satisfies this. Of course, there could be some constant in front. We don't care because right now we're just trying to find out a function of this form, some function of x times function of t. And once we find them, then we're just going to put some constants in front of them and add them up for n equals to 0 to infinity, and then that summation we hope to satisfy the initial condition also. Okay. All right. So this is what we have so far. Since this is your t and this is your x, we have uxt equal to e to the negative 7 n squared pi squared t over 64 times cosine n pi x over 8. And for those people who are struggling to find out what's going on, let me try to explain a little bit here. So if you have this, this is going to satisfy this equation, the heat equation. You can check. If you differentiate this once in t, and if you differentiate this function twice in x, and multiply by 7, you'll see that these two are equal, if you do it. So this certainly satisfies the heat equation itself. It also satisfies the boundary conditions, these two conditions. Okay? Because if you plug in 0 into, if you differentiate by x, you get sine of something like this. And when you plug in 0, sine of 0 is 0, so it does satisfy this condition. And same thing for this one. If you differentiate, it will still be n pi x over 8 with sine. When you plug in 8 into x, it's going to produce sine of n pi, which is also 0. So this equation will satisfy this one and this one, but not this one. Because, see what you get. If you plug in 0, what do you get for t? 0 for t. This goes away, and you get cosine n pi x over 8, right? That's what you're getting, and therefore that's not the same as negative x plus 6. So that doesn't match with this one, and therefore it doesn't satisfy this one. So, I mean, we kind of managed to solve a lot. We found the solution that satisfies this and that, but not this. And you might say, how do we make this work? And here's the idea. If this is the solution, because these conditions enable you to find summation of all the solutions, and it will still satisfy these, we can just take all the sum of these functions. Okay, so let's try that. So that's the second step, I would say.
Taking the sum of what?
Sum of all these. Okay, so we're just going to say, so this one, we just got it by assuming that u is a function of x times function of t, but in general, you wouldn't expect that to be true. We were kind of hoping for some miracle, but even though the hope was too much, we still got something substantial. It was good enough that we can now say uxt must be sum of n from 0 to infinity of some constant Cn times e to the negative 7 n squared pi squared t over 64 times cosine n pi x over 8. Okay, so that's your uxt. And I mean, we've done this before, right? In constant coefficient linear homogeneous differential equations, when we found a solution and another solution, what did we do? We took C1 times the first one plus C2 times the second one. That was the general solution. That's how we did it, right? The only difference between that one and this one is here we have n from 0 to infinity, right? So you have infinitely many of these solutions. So you have to add infinitely many with Cn's. Cn's being arbitrary. That's what we have to do. Okay? So instead of just C1 and C2, we have C0, C1, C2, C3, up to C infinity. Okay. All right. Now, this will still satisfy these two equations, no doubt. Right? If you don't believe that, you can actually plug it in and see if it works. Okay? It will work. Okay? The only trouble is, does this work? So let's see what we want. What is ux of 0? Ux of 0 is sigma n from 0 to infinity of Cn. E to the 0th power is 1, so you just get cosine n pi x over 8. And now we have a problem of trying to find out what Cn is. See, if you have a general solution, C1 of some function plus C2 of some function, you have to plug in the initial value to find what exactly C1 and C2 is. If you find the C1 and C2, that's the end of it. You have the solution, right? Same thing here. If you know what CNs are, then that's it. You plug it back into this formula, and that's the end of the story. You have the solution. Okay? So our goal is to find Cn. But when did we ever do this? Writing a function, which by the way is negative x plus 6, writing a function as sums of cosines. What's that called? Fourier cosine series, right? And that has to be valid. I should have written some inequalities here. So this should be valid from x between 0 to 8. This should be valid from t greater than 0. These are some customary inequalities that you add on. So because you want this to equal to this one for x between 0 to 8, you're basically trying to find the Fourier cosine series of this function in this domain. So let's find out an. This is 2 over 8, 0 to 8. The function is negative x plus 6 times cosine n pi x over 8 dx. That's what we have to compute. Now, although it's the same formula for both a0 and an, we know that we have to calculate it for two different cases, right? a0 has to be calculated separately. We learned that while learning Fourier cosine series. Okay, but let's do an first, and then we'll come back to this with n equals to 0. That will be a different calculation. Okay, so we have plus minus d integral negative x plus 6, negative 1 and 0. Then cosine n pi x over 8 integrates to sine 8 over n pi sine n pi over 8x. And integrating this again, you get negative 64 over n squared pi squared cosine n pi over 8x. And then this is plus minus plus. And then going like that, you get negative x plus 6 times 8 over n pi sine n pi over 8x. And then going like this gives you negative, 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 that's still negative. 64 over n squared pi squared times cosine n pi x over 8. And the real tabular integration, you have to multiply the end and you integrate, but this is 0 times something, so you don't get anything when you integrate this. Alright, so that's what you get if you do integration by parts or tabular integration. You can do either, you'll get the same answer, and you have to plug in 8 and 0, and then don't forget this 1/4. 2 over 8 is same as 1/4, right? So you have to multiply 1/4, whatever you get here. You plug in 8 or 0 to sine. In both cases, you get 0. So the only non-zero thing that you get is from here, right? When you plug in 8, you get cosine n pi, which is negative 1 to the nth power. When you plug in 0, you get 1, which is just 1. And in both cases, the coefficient is negative 64 over n squared pi squared. So I don't really have to, I can just factor this out and make it like this. So this plugged in gives you that. This plugged in gives you this. If you subtract. And taking 1/4, a fourth of 64 is 16. So we have a really nice result. The result is that an is a fourth of 64 is 16. So it's negative 16 over n squared pi squared. Negative 1 to the nth power minus 1. So that's our an. Now what about A0? A0 is, let's see, that's 2 over 8, still the same, 1/4. 0 to 8, negative x plus 6 dx, which is 1/4 of negative 1/2 x squared plus 6x, and you're plugging 8 and 0. Let's see, if you plug in 8 times 8 is 64 divided by 2, that's negative 32. And when you plug in 8 times 6 is 48, 48 minus 32, that's 16, 16 divided by 4 is 4. So that's what you get. And now you can rewrite negative x plus 6 as a Fourier series in the following way. So both of those calculations can be now written as, what is it? A0 over 2, so it's 4 over 2, plus sigma, 1 from infinity, from 1 to infinity, of an, which is negative 16 over n squared pi squared, negative 1 to the nth power minus 1, times cosine n pi x over 8. All right, so what does that teach us? That C0 is? See, these two should be the same. So C0 is? What's C0 attached to? C0 times cosine of?
Oh, so it's 16,
0.
negative 16 over n squared,
Is it
pi
a?
squared.
If n is 0, C0 is attached to C0 cosine of 0, which is C0 times 1. So C0 is by itself, if you expanded this. Over here, what's by itself? A0 over 2 is by itself, right? So C0 is?
4 over 2.
4 over 2, which is 2. Okay, 4 over 2, which is 2. And then Cn is?
AN?
Cn is same as this much. And this is your Cn for n 1 or greater. Okay. So that tells us that we actually have the value of Cn that's different when n is 1 or greater and when n is 0. So those two should be done separately. Okay, but that's good enough. Now we are ready to write down the final answer. What's the final answer? So answer. Okay. UXT is, for C0, what is it attached to? It's attached to this, but no cosine, right? So, no. The n is also 0 here, so that's e to the 0th power, cosine of 0th power. Cosine of 0, so that's 1, that's 1. So C0 is by itself, even in the original entire sum. Okay, so UXT is C0 plus sigma of n equals to 1 through infinity of Cn e to the negative 7n squared pi squared over 64t cosine n pi over 8x. And then C0, because that's equal to 2. And from 1 through infinity, we know that Cn is this horrible thing here. It's negative 16 over n squared pi squared negative 1 to the nth power minus 1 e to the negative 7n squared pi squared t cosine n pi over 8x. How much time do I have left?
46 seconds.
Okay.